зараз воно пишеться в YouTube, от зараз пишеться, а там затримка до 4 хвилин. Студенти питання не могли задавати. Ну, то ми зберігаємо для тих, хто не попав, там Мирослава за кордоном не може. А окремо буде трансляція інтерактивна з ноутбука. I'm talking about those delays and whatever, there's problems with translation. Та-та, ну devices for students. I'll come late because I have talked with Pan Vasily about our business here.
Good stuff, yes.
Yeah.
Business here, I feel we are going with my colleague. We must talk about new project, a project for young research. We must talk about it. We must build plan to realize this project.
Good.
Камера and Plaza for Yura who perform translation.
Oh, okay, good.
Do you need markers?
No, I have in my packet.
So,
I think I was going to start this with telling them that in my own, I'm just curious what you think. In my own career, I learned machine language first, and then assembler, and that has helped me all through my career. I can't think of anything better than learning assembler.
But it was changed a little bit from maybe opposite direction.
Yes,
But I think assembly is necessary.
Yeah.
I have interpreted to assembler CPM.
Yes. Yeah.
No, and I learn it, students, and have good results because this assembler is simple.
Yes.
And
I'm sorry, but I have the chip for this assembly. But here is my backpack. I'll show later in course of our talk about it.
Yeah.
So, I will return.
Okay,
But
we'll
I
back.
need to...
Okay, I'll see you later. Okay, thank you. So good to meet you. Yeah. Okay, see you later. Oh, here it is. Oh, hi, how are you? Hello. Oh, today's gonna be fun.
Yeah.
It is, it's gonna be a summer. This is.
I like.
Where do I click on this? Oh, just.
Yeah,
Just pause it.
Бо я такої камери в житті не бачу. Камера.
Okay. You guys got stuff from your, I sent?
That you said? There is some presentations yet.
Yes.
Yeah,
But you
we got
can,
it.
we'll talk about it here, and everything I have here you can copy.
I just will connect some.
One of you guys have a Windows machine?
I have it home.
Yeah?
I have it home too.
What's on that? Linux?
Yeah, I have Linux and he use Mac.
Okay.
I can download Windows.
Oh, no, what I'm looking, there's I've got a couple simulators I found, but one of them goes on to Windows. I mean, if somebody has Windows, if they could try putting it in and just see if it works, then I'll figure out something in the meantime.
Lose the command line. That technology is something. This is kind of
The UCB hub.
I will ask some people who will join us.
Good.
Come bene, vado.
Возбуждание сегодня. Слишком по-английски. As usual, как я все работаю? Я не понимаю. Да, разбирайся. Давайте без таких английских рупов, пожалуйста. Я, конечно, понимаешь. Думаю, як я. Там. Что моя камера?
Я поняла, что ты ставила другая.
Присоединиться. Можно ли еще тоже ще може приєднатися? Hello.
Is that Roman?
Yes.
Hi, Roman.
Hi, Jim.
You're gonna have a lot of fun today. This is assembly time.
Assembly
I
time.
sounds like
Assembly time. Окей. Так. Тільки я маю на камеру ще настроїти, секунду. I just need to set up this camera.
Yeah.
I don't know how to do it. Чистирование камеры. No, okay, whatever. It's not working, so I just turn my PC on.
Well, I'll get started. Well, first of all, I want to give a little sales pitch about why assembly is good.
Підняти таку руках підняти. Так?
так.
Вруби камеру, щоб вже тебе бачити, так буде получше. Ні.
Там тільки тросак.
Опа. Ні.
Ти не показав нижче.
Виїв футболка. Окей.
Да, я хлопцы, все равно.
Oh, hi, how you doing? Actually, very good. Hey, when I started, this is many years ago, first electronics and then with computers, I actually started with machine language and then assembler and then the higher level languages. The assembler and the machine language actually has helped me my whole career. That doesn't mean I'm always programming in assembler, but that knowledge of assembler helped me understand what's going on when I made mistakes. I've made thousands of mistakes because I've had a lot of time to make them. What you have to be able to do in our business, this IT, is find mistakes, diagnose them, and correct them. So the biggest thing you have to do is correct your mistakes, or somebody else's. Assembly helps that a lot. So, helped me my whole career. So anyway, let's get going on this. We'll be talking about assembler. In your things that I sent was something called a System 370 reference summary. I'll just point it out now, but you'll probably use that a lot, or at least take a look at it. This is 370, there's also 390, but it's much, much larger, more pages. And let me go over this first of all, just so you get an idea of this. And it's like a card. The people in the business, these actually used to be colored green on the original IBM 360. So now they call these green cards. And they're good, big enough to fit into your shirt pocket. So what's in this? I'll just go through real quickly. It'll list all the names of all the instructions, each one of these machine instructions. It will tell the mnemonic. So compare register. The opcode in hex is a 19. The format of the instruction is register to register. We're going to learn all about this. And this is, if you have, how you would code it. You would code it in this format. And we'll learn how to do all that. This is similar to learning a language. Like, you know, thousands and thousands of Ukrainian words. But you can also communicate in English, where you have just a small subset of words, I think. Well, the same thing with this. There's hundreds of instructions, but you could do a lot of coding with about anywhere from 50 to 90. So we don't need to learn all the instructions. We'll learn a subset that are mostly used. So although we see a lot of instructions, don't worry, we don't have to memorize all of them.
It's similar to acronyms, you know?
Into what?
To acronyms.
Yeah. Similar to acronyms. So there's a bunch of instructions. They do all kinds of things, most of which we'll never use. There's condition codes. Condition codes mean if you do an arithmetic instruction that usually says a condition code, and it'll say the result. Is the result 0? Is it positive? Is it negative? Or is it something bad like overflow? Will be described here. So these instructions are, the first one are by alphabetical order. They're grouped up here. We'll just keep this one along. There's other things on this card. You can just look at it. You don't have to get an idea of what's there. These are constants. We're going to learn some of these. Like C means it's a character. X means it's a hexadecimal. Binary, full word, half word, floating point. We're not going to do floating point. I've never done floating point in my career. I studied it, I'm ready for it, but I never did.
It's good to know.
Yeah. There are several forms of decimal numbers. Keep in mind, these IBM mainframes are used in business. And business doesn't use floating point, because floating point
Unstable.
sometimes can give you approximate answers. No one wants to know the approximate amount they have in their bank account. They want to know to a penny. So we're going to be using decimal formatted numbers. There's several formats for decimal numbers, we'll learn those. Other stuff that we won't cover, but it's on this card, just to tell you about it, is we can send certain commands to devices like printers, disk drives, card punches even in the old days, and that's what all this is about. And again, I've rarely in my career used this. These are channel command words that we talked about. Again, it's extremely unlikely that you'll ever write any of this. This is very useful toward the end because you can use this, if you don't have your calculator around, you can use this for a human 10 equals a hex 0A. The 0A can be used in, oh, I picked the wrong one. Let me do like 60. Okay, this is what I'd love to do. Okay, so a human 97 is equivalent to a hex 61. In EBCDIC, it's a lowercase a. So here is a good place to, here's a human, hex, and really if you're kind of slow, you can figure out the binary. There's just pay this all the way up to 2 bytes, which is 256. So FF equals 255.
And you said that in new architecture there is more pages?
Oh yes, because they have hundreds and hundreds more instructions. Most of which you won't use. Okay. No, there's a lot of system programming uses of it. The compiler will use those, but normally you just wouldn't use this unless you're doing very specialized programming. Over here, this is what we will use. Machine instruction formats. So if you look inside the memory, the electronic eyeballs, you're going to see instructions, and the instructions will be in one of these, for us, 6 formats. The newer machines have dozens more of instructions. But we'll be using these instructions. RR, register to register, register to index storage, storage to storage, I'm sorry, register to storage, and there's a couple of storage to storage instructions. You know, we'll see those as we go along when we look at some of the instructions.
And what kind of command is like if we want to call printer? So it's...
We're going to learn that. Yeah. But if we're going to write to a printer or read from a file or write to a disk drive, we're going to use something called a macro. So we're going to have an open macro, like a put, get, macros. So we use macros. The system will expand those macros into typically a large number of instructions. And we'll take a look at that, see how that works. There's something called a PSW, Program Status Word. It is 63 bits long. What we're concerned about in our work here, we'll be concerned about two parts of this. One is the instruction address. Now, the program status word is in a register in the central processor. And it's pointing to usually the next instruction that has to be executed.
Like previous pointing.
Yes, every time you execute an instruction, you read the instruction, and this guy moves to the next instruction. Execute it, moves to the next one. So it's always pointing to the next instruction that has to be executed. There's a couple.
Jim, can I have a question?
Yeah, sure.
In that I read, there was said that there is three program status words like current, old, and new. And where is this status words in the computer?
I understand, it's not. There's only one instruction address register. But you should be thinking about the previous instruction, the next instruction, and the current instruction. There's only one instruction pointer. Okay. And we're going to see this real soon. Okay, channel command word, we're not going to be doing channel programming.
It's like to move input output.
Pardon?
It's like for input output channel.
Yes, the channel is for the channel subsystem. Again, the only people that be coding this is somebody at IBM.
No, to improve.
Or, yes,
To improve I/O. No.
you're going to call an access method like the sequential access method. That program will build a channel program.
Okay.
Okay, so the only guys that are using this, for the most part, that are not working on the IBM operating systems, would be somebody who's building a plug-compatible disk drive, because that disk drive has to accept what? These channel programs to do whatever it's supposed to do. One thing that you're going to get involved in, and this is, you probably won't make any mistakes coding, but if somebody else does, what'll happen if they do things wrong, typically one of these program interrupt codes gets activated. Typical ones are a 4. 4 is a protection exception. So your program is pointing to someplace where you're not supposed to be, like the operating system code.
And can you somehow overcome this exception?
Nope.
Anyway.
No, unless you're like a supervisor. But again, you're not going to be supervisor in the type of coding we're going to be doing. We're going to be in user mode, basically. Like we're in ring 3, not ring 0.
If you want to destroy something, it's like.
Yeah, the whole machine is built so one of these 100,000 people that are using it right now do not stop the machine. So
it's possible to overcome this exception.
Pardon?
It's possible to overcome this exception.
Yes, what will happen is that it'll get like that would be one. Divide by, here, a decimal divide exception. Okay. You're dividing by 0. So if you get divide by 0, you get a return code of B, and the operating system will interrupt your address space, stop your program, and give you messages, and usually a dump also if you request it. So it'll dump out your program area in virtual storage. So between the messages and this dump, you should be able to debug your program, find problems. Good?
Yeah.
Oh, that gets into that instruction address register. If something goes wrong in the program, we're going to look at the contents of the instruction address register because it's pointing to the next instruction. We're going to back off and say, ah, that's where it went bad. There's some fixed storage locations, so that's it. Oh, worthwhile.
What is that?
Okay, with 8 bits, you can address a number from 0 through 255. So 8 bits can address 256 places. The other one that you'll remember is 10 bits, it's 1K. 20 bits, 1 meg. 24 bits, 16 meg.
You're looking for 24?
Yeah, I'm looking for 16 meg.
16
31.
for power 5?
I'm looking for 31. It's on the next page.
No.
It takes the last 10 page.
Might be the last one. Okay. 31 bits, you can address up to 2 gigabytes. So 2 gigabytes, 31 bits, 24 bits, 16 meg. The biggest ones that we'll be talking about here. Well, I'm going to get to the slides now. We'll talk about those slides. Let's see. Whoop. I got this off the internet on Dr. Wilbright's site. And as I said, he teaches at Columbus, Georgia. And there's a large IBM shop over there. Well, just a little intro to this. You guys can stop me at any time if you don't understand what I'm saying, I'm using a word you don't understand, or just need something repeated, or I don't get it. It's important that you do that because as I'm going along with this, everything will build on the first. So as you go along, everything's building, building, building. I don't want you to miss out on anything. Well, this is things we talked about already. The IBM mainframes, old architecture started in '64, and here we are in 2018 with the Z architecture. There's 2 important manuals. One is the principles of operation, but I kind of find most of the things I find out about are on that green card. Here's the green card, which is an IBM 360. We're using the IBM 370 that I gave to you. There's also another book called Principles of Operation. We'll take a look at that the next class, the contents of it. What they'll do is, if you're designing a computer that works exactly like IBM's, you'd use that book. It describes every instruction in excruciating detail. A lot of times we just call that POP, pop. The pop is the principles of operation. There's a lot of documentation on all this stuff online. I'll try, my goal is to give you a subset of assembly, enough to kind of to do useful things, and it should suffice the rest of your life. It'll be a basis of learning.
Will we do some tasks?
Pardon?
Will we do some tasks?
Yeah. I want to talk about this very quickly, and the way this all works is a programmer writes the assembly source code. That goes into the assembler and creates an object module. The object module has, you can look at binary, but my view of it is usually in hex, and yours will be. It's in hex. That ends up going to something called the binder. Binder. It goes to something called the binder. And it used to be called a link editor. It did linking and editing of the object module. Did you guys talk about that in one of your earlier classes?
We didn't talk about, me and Roman, we know it from online classes.
Oh, okay, good.
It was also on this online course.
Okay, good. We may review it very quickly just to make sure everybody's at the same place. That ends up with the load module. The load module, there's between the load module and memory, main memory, is the loader. So the load module is sort of like the exe file that you have in your PC. So that the contents of the exe is input to the loader. The loader is going to think about what's in there and actually put a program in memory. And then start execution. So we'll get some ideas of how that works as well. Just bit is a single binary digit. Byte in our world, almost everybody else's world nowadays, a byte is 8 bits. Historically, that wasn't always true, but it is now. Bytes are very friendly with each other. They like to hang out together, and they hang out together mostly in full words. A full word is 4 bytes. So that's all you got to remember. Because if somebody says half word, what is that? Full word is 4 bytes. Half word must be 2 bytes. Double word, quad word, same thing. If it's a half word, then it's going to be on an address. If it's on a half word boundary, a lot of times we're concerned about where either data or an instruction is in main memory. Main memory has addresses. If the address is evenly divisible by 4, that's a full word boundary. If the address is on an even number, that means that address is on a half word boundary. Everybody follow that?
Yeah.
So it's a lot of instructions, a lot of times data needs to be placed at a certain place in memory. We call those boundaries, and the boundaries we're usually worried about is full word, half word boundaries. Sometimes double word, not common. We describe this memory, they've got these kilobyte, megabyte. The only other thing I have to say about this, it's sort of a standard. If you write K uppercase B, it's number of bytes. If it's a lowercase b, it usually means bits. So a K lowercase b would be 1,000 bits, 1,024. There's a little definition, and you have to understand that by context, that 1,000 kilobytes, we don't know if the 1,000 is calculated in base 2 or base 10. So this illustrates this. 1 kilobyte is 1,024 bytes in our world. But when you're buying machines and memory, disk drives, sometimes they're using a kilobyte is 1,000. So they kind of sneaky, give you a little less, the vendors. So they have these terms. We're going to be representing memory. You guys are okay with binary to hex, right? 1101 is a D. 0110 is a 6. And that's illustrated on the side over here. Okay, C is 1100. Okay, F. So now we get going. In our machine, there are 16 general purpose registers. The system Z, those registers are 64 bits. They're used for binary arithmetic. They're used for creating addresses. These 16 registers are numbered from 0 to 15 human, or 0 to F. We'll be using mostly 0 to F. We'll be going back and forth quite a bit. We'll be taking a look at most of these. We won't be using all 64 bits. For the most part, we're just going to be using the right side, 32 bits, in our instructions. Keep in mind, the new machines, they are 64-bit. We're going to be using the right-hand side. The rightmost, 32 bits, you can look at it just as a 32-bit register, and that's what we'll be concerned with. So we're going to have a lot of instructions that will have to specify an address. Now, how that address, sometimes it's calculated, it's determined by 1, 2, or 3 things. What are those things? 1, it could just be a relative address, like 2K. Wherever I am, 2K more, or 4K, or some number in between. Sometimes it's calculated by the contents of a base register. So in our program, we're going to select one of the 16 registers as a base register. Usually, by convention, it is register number 12. So we're going to use, in most of our programs that we'll be doing, the base register will be register 12, and it will contain an address. But to calculate the address that the instruction will use, some of them use the contents of 12 plus a displacement. The displacement can be anywhere from 0 through 4K. 4K 4095. Sometimes, on some instructions, the address will be calculated from 3 things. The base register, in our case, will be usually 12. plus a displacement, just like this guy, plus the contents of another register, general purpose register, and we'll refer to that as the index register. So let's say we're going to go through an array. You want to keep marching through that each time. So you start off with the index register contains 0. The base register plus the displacement will contain the address of the start of the array. And then if each element of the array is 16 bytes, we're going to be adding hex 10 each time. Each time to what? The index register. So it'll be a way for us to go through an array. Questions? Roman, how you doing?
How would it
Hmm?
Good.
This base displacement scheme is used for three things. One is it will make the code smaller. Second, it will make linkage simpler. Linkage means we're running one program, we want to call another program. The linkage, that call is called a link to the other program. So it enables linking. It also allows our programs to be relocatable. Did you go through relocate in your other class? Roman?
Relocate. Не спал.
Like when you need to call a system some programs?
Yeah, so relocate means this. I don't know where my program's going to go in memory. Now, on your PC, a lot of times, you don't need that relocatability. Your programs can start at one place every time. But let's say I already have a program running in one area of memory. I've got to load another program. I can't load it at the same place. I have to load it someplace else. The next time I load it, it may load someplace else. That's relocatability. So I can put the program anywhere in main memory. Base displacement addressing allows me to do that, and I should have. You can add over here relocatability. So you take the contents of the register plus a displacement, we can calculate an effective address. Sometimes you take the contents of the base register plus the contents of an index register plus the displacement, those three things, and get an effective address. Good? We're beating this to death. I don't want to spend that much time on it. So let's say our reference point is at address 1500. If the displacement is, the address is at 005, the effective address of this position in memory is 1505. The contents of the base register plus the displacement.
And how to calculate the displacement?
Pardon?
How we calculate the displacement?
We'll show you that. What we're going to do is we're generally going to let the assembler do the calculation for us. But we should be able to do this by hand.
That's why I asked.
So we'll show you how to do this as we're covering the instructions. We're going to be concerned with the 31-bit addressing in our class. 31 bits can address up to 2 gigabytes of memory. That's pretty good. Get this right. Program can change address modes. That means go from 64-bit to 31-bit, 24-bit, depending on the instruction. We're not going to get into this much type of coding. We'll always be running in the 31-bit address. System Z has well over 1,000 instructions. I think our subset that we're going to be looking at is from the System 370 days. There's maybe about 300 or 400 instructions. And out of those, we'll be just using a few dozen. Instructions, there's types. And although they talk about types, these are really the format of the instruction. So these are the format of the machine instruction. We have an our register to register format, index storage to register. So here's 2 operands.
Now from right to left.
Yeah, each operand is in a register. Generally, the specification will be from right to left. There are some exceptions, and you will learn those. Rx means what? One operand is a register, and the other one is indexed storage. So this would be a displacement, an index contents, plus a base register contents. You add the 3 up. Register to storage.
Storage to register.
Now, storage is displacement plus the base register contents. Store to store. Oh, this is interesting. This is a skinny, a tiny instruction. And it's going to take an immediate operand and put it into storage. The operand is not someplace in memory. The value, there's going to be a 1-byte value in the instruction. And that's going to be put into a storage location.
To set the variable or something?
We could do, yes, we could set a constant typically. Okay, same thing. Register to register. Register to index storage. Register to storage. Storage to storage. Storage immediate. This, not the instruction, but the value, a 1-byte value, is in memory. I missed that, I should have changed it, sorry. The program status word, we're going to be worried about 2 parts, or concerned with 2 parts of it. We're going to be concerned about what is the current address. So this is pointing typically to the next instruction. The other thing we're going to typically be concerned with is the condition code. You see, bit 18 in June, 18, 19, 2 bits. How many values?
2 bits. For 2 power 2.
Do you agree with that? Roman? You don't think it's 6?
I don't know.
Okay.
Two-power two, Roman.
You have to pay attention.
Muito irritado.
Two bits for condition code, 4 possibilities. Some instructions will change the value of those 2 bits. Many instructions do not. We'll learn which ones do. The reason for these condition codes is that it will, they'll be used, the condition code contents will be used in branching instructions. So here we have compare logical characters. We have a string of characters. A, B, C, D, 1, 2, 3. We're comparing them. If they're equal, so when we do compare, what happens? The condition code is set. If they're equal, the condition code will be set to a binary 0, 0. Branch equal instruction, what does that do? One thing, looks at the condition code. If the 2 bits are 0, 0, it branches to this address. If they're not equal, then it just does the rest of the instructions. We're going to learn and see how this works. I'll expand on this a little bit about the instruction address. It's usually pointing to the next instruction. So, we're going to go over here. I want to talk about, hardware-wise, how the computer executes an instruction.
Рачика добре?
Yeah.
And what we're going to do is, we're going to find out what pipelining is. So, how does a computer execute an instruction? First is so what we have is the instruction address register is usually pointing to the next instruction. So we just finished an instruction, just completed it. What happens? The instruction address register is pointing where? Into memory, to the next instruction. The hardware does a fetch. It goes into memory. And it gets the instruction from memory and puts it into the instruction register. The next step it does is a decode. So it looks into the instruction register, and one of the things it finds out is what does the instruction do? Very importantly,
But it's constant length, no?
so the instructions that we're going to be dealing with could be a 2-byte instruction, no, that's okay. A 4-byte instruction or a 6-byte instruction. So, fetch, computer goes into memory, where in memory? the memory that's pointed to by the instruction address register, goes to that location, gets a few bytes, and puts it where? Into the instruction register. Now, it doesn't know how long the instruction is, so it has to look at the instruction, the first byte. The first byte will tell it, is it a 2-byte instruction, a 4-byte, or a 6-byte instruction? Once it knows the length of this instruction it's pointing to, it goes, oh, you're a 4-byte instruction. And does what? Adds 4 to the instruction address register. Now this guy's pointing where?
To the next instruction.
To the next instruction.
And why do they does it in the middle work? Why not in the end?
You'll find out. So this is called the decode step. So the PSW now points to the next instruction. If the instruction failed right now, like you did a divide by 0, or you did an overflow, what would happen? It would stop, and the instruction address register won't be pointing to the instruction that failed, it'd be pointing to the next one. Now the next thing is we're going to execute the decoded instruction. We know what the instruction is supposed to do. Now we're going to do it. But there's several phases to this. So we have an add register instruction. It's going to do what? It's going to take the contents of register 2 and add it to the contents of register 1. This is called an opcode.
Like a plus.
Or an operation, and these are called so words you have to remember: opcode, what you're going to do; operands, who you're going to do it to. So part of the execute, there's several parts of this. Get operands. Whoop. Apologies. To get the operand, if it's in a register, you're all set. Just go in that register. Well, what if the operands are in storage? So it's got to calculate where are those operands, and sometimes they'll be
Okay, if one instruction fails, then the PC goes to the next instruction.
No, it's already pointing to the next instruction, it stops. And you get a report saying, here's the address, here's the contents of the instruction address register. Here's where the program loaded. Here is the contents of the instruction address register. You've got to figure out what instruction that is and back off of them.
Okay.
Very sneaky. During the execute, you got to get the operands. To get the operands, you got to calculate where are those guys. So a lot of times to get operands, there's a little calculation. That's done in the execute step. It gets the operands. So it does whatever it's supposed to do. If it's a move, it's a copy, whatever it does. It's got to get the operands. To get the operands, it's got to calculate the addresses. After it gets operands, it's got to do something with those operands. If it's an add instruction, then it needs to take the result and write it out someplace. Starts again. Right now, the instruction address register is pointing to, it's all set to do the fetch. Okay. Are you guys very clear on this part?
Yeah.
Yes? So, how can we speed this up? I don't have extra memory. So what I showed, illustrated right now, was how to execute one instruction. Let's execute 5 of them all at once. How are we going to do that? We're going to make several boxes. We're going to make a fetch box. There's a bunch of hardware. Little decode box, more hardware.
And why is it faster?
So what I'm going to do is, hardware-wise, I'm going to have several pieces of hardware. An instruction is going to come in and do the fetch. So this guy is only set up to do what? Go into memory. Where in memory? Pointed to by the instruction address register. And get the instruction and put it into the instruction register. Then it moves on to another piece of hardware. That's going to figure out, like, how long is this guy? What does it do? So the instruction comes in, does the fetch, the instruction moves over for the next part of its execution. What is fetch now going to do? get the next instruction. So now the first instruction is at decode, the second instruction is at fetch. They all move over one. Now the first instruction is doing calculate operands. Second instruction is doing the decode. The third instruction is being fetched. Execute right. So you can see that I can have 5 instructions. So every clock cycle, I'm executing 5 instructions. Roman, you can explain this to your grandmother?
I could explain, but maybe she won't understand.
Well, you can try. Okay, does this make sense to you, Roman?
Yeah.
So this is called pipeline. Now, when doesn't this work?
When it's less than 5 instructions.
If there's less than 5 instructions, but you wouldn't know it at several billion times a second.
Maybe when one instruction is working more much time than the other instructions.
That could be, but usually that's not the case.
Maybe when some instruction fails and then another instructions don't know what to do.
Roma, slow branch.
What about a branch instruction, Roman? Why would this not kind of mess up this whole thing?
What is a branch instruction?
Well, it branched, if the result, if this, where's the next instruction? You guys had, Python. So what does this say? If there's a condition, don't do the next thing, skip it and go someplace else. So, okay, you follow this?
Yes, and we are already fetching the A instruction.
Yeah, you're fetching the other one, you go, hell, it's a branch instruction, I gotta flush all this and start over again.
Yeah, okay.
Roman,
Yeah,
Включи
what
камеру.
does yeah mean?
Покажись.
I understand.
Так, включи камеру, так легше буде.
Що маю сказати?
Та включи камеру.
Why do I have to flush the pipe, Roman? I just did a branch, and the branch wasn't to the next instruction, it was someplace else. So why do I have to now flush the pipe? Flush means empty it out
Понял?
and start all over again.
Ром, якщо в нас є івка і там є condition,
Ну, я
ну це одна, типу, інструкція. А в івці, типу, є перехід до 2 наступних. Тому чому пайплайн може бути фіговий через то?
Because the time that we wasted on that instruction is wasted.
The next instruction in the pipe will not be executed.
He understood it. It's like,
Got it? Okay, good. So, there's several ways computer manufacturers get around this. One way is to have more than one pipe going on. Like I worked on this stuff all, even up to the 80s.
Okay, different types. In one time, like forward declaration of A and B.
Right. So you have another pipe, and if it happens to be if the decode says, hey, this is a branch,
And
then what it'll do is it'll go to the other pipe, and now you're running both parts of the branch. It's either going to be do A or do B.
And how the pipes are connected? Like how we can go from one pipe to another?
Once it finds out what the operands are and what to do, then it'll switch over to the correct pipe.
In the execution.
I'm sorry, I'm pointing the wrong place. Yeah, in the execution.
And
And then the right is doing what? It's writing the next address into the instruction address register.
Okay, Romчик, continue.
Jim, when
Yeah.
we have a switch instruction, so we can have as much these pipes as we need.
No, they're hardware and you pay for them. So manufacturers have different strategies on how to do this. And I'll give you an example. I worked at Amdahl. We made plug compatible machines. IBM was like Intel. We were like AMD. Follow?
Yeah.
We made the exact same operating chip, different manufacturer. So IBM, they did this thing with, when I was there, they had 3 pipes. We figured out how to look ahead, sort of like, of what's going to happen with these conditions. So what we did is when we were in competition with IBM at a customer, we would try to get jobs that did a lot of branching. Try to win the competition. Make sense? So nowadays, they have a couple strategies. They also, have several pipes, but also that the electronics is much less expensive now. You can make more complicated electronics that they can kind of look and predict how the branches will go.
You had a good rival.
Yes. So, okay. So I wanted, this isn't in here, but I wanted to get the concept. There's a few concepts I want to get to you guys. You're not going to be designing machines, I don't think, are you? Maybe. Probably not, unless you're electrical engineers. But this pipelining is an important concept to understand. Okay, let's go back. We do a fetch. Fetch does what? Gets the instruction from memory. Where in memory? What is pointed to by the instruction address register? At that point, what happens? The instruction address during the decode learns how long the instruction is and increments the instruction address register. This will be less detailed than maybe what I did. It's going to get the instruction, execute it, go to the next one. All machines do it, work this way. Now, how does branching work in this situation? Branching changes the contents of what register. When you branch, what is being changed to cause the change of direction of the program?
Can you repeat one more time?
When you branch, not you, the computer, when the computer, I'm treating you like a computer, not fair. When the computer branches, what register is getting changed to cause that branching?
Logic.
So if a condition code, then normally no branching.
Yes.
But in this case, if you go to B in the program, what has to change?
No, okay. Next instruction.
Right. So what branching does is changes the contents of the instruction address register.
Okay.
Very good, good. Good. We're going to code assembly statements.
Можно повернуть.
The
Технология.
the record is going to be 80 characters long, 80 byte record. We will use columns 1 through 71 to code an assembly statement. Column 72, usually they just put X for a continuation. But any character in 72 says continue this to the next statement, or the next record.
And the last 7.
These last ones are usually empty. Historically, they actually had punch cards for this. And what they did in the last 7 bytes, 8 bytes, is put in a sequence number. Because as you're walking along with this big bunch of cards, what happens? Whoops. And that way you can get all the cards back in order. So nowadays they don't really need that. So, column 72 is the continuation. Before people quit, they're usually writing little messages here. 73 to 80, just the continuation. 16. Oh, when you do continue, you continue at column number 16.
Not the next statement.
Yeah, and the next statement, you continue on the next card at column 16.
And then 1 and the next one.
And then if you have another statement, you'll start over here.
From first.
It won't have a continuation. I'll show you examples of this. Matter of fact, no, it's not. So here's an example. It may or may not have a name for that statement. Compare logical characters.
Operation.
Operand 1, operand 2. These are 2 places in memory.
Comment.
And maybe a little comment. Empty. From 72 to the right, empty. The operands are, so they're a name, space, the opcode, the operation code, space, operand, comma, operand, no spaces. If there's a space, then this is comment.
Yeah.
Okay, the name of the instruction, that's this guy. It can be, it has to be either alphabetic or a national character. Make them alphabets. The rest can be alpha and numbers. But the first character has to be alpha. The assembler is kind of human-like, so it can have a symbolic operation code like A for add, AR, add register, things like that. The operands are names, sometimes, that are meaningful to you.
And if we use macro for our devices, they can differ from one device to the another, no? Or
Right, I'll show you how that works later. Right now, a macro is going to expand into a number of assembly statements. Okay. Usually, you don't expand the macro. You just leave the one, like put. You leave the one statement. MVC, you name this one address X and you gave a name to this other address Y. Comment. Kind of a
like equal.
stupid comment because you're moving characters. Of course, you're going to move from here to here. So here you usually write print buffer to print out, something like that. Something that would help somebody read what you're doing. If you're doing a payroll, I don't know, like if you're doing a payroll or something like that, you'd say calculating hourly rate. We'll be using EBCDIC coding for characters. The letter A is C1. You get used to looking at these in dumps, you start remembering what these are, but you don't kind of worry about them too much. But it's worthwhile knowing that A is C1, and there's an order to these. Uppercase.
We don't know Ukrainian alphabet, so
Oh,
maybe we don't know this one.
well, you'll be good at this by the time you get done. Okay. The numbers, now these are not the value 5, it's the character 5. A character 5 is a F5. A character 0 is F0. So these numbers are easy to spot. You included this, I'm not sure why, but there's Herman Hollerith, there's a card.
Well, whatever.
Okay, you can go to history, go to museum and see this stuff. One of the things we have to do, we have to tell the assembler not only what machine instructions to execute, we also have to tell the assembler, hey, I'm going to be using some data. Or I'm going to use some of the data, I'll define it now, it will be a defined constant. Some, I just need buffer areas, I need some areas of memory. And we have some defined storage and defined constant. The defined storage can be a maximum of 4K. Defined constant could be a maximum of 256
In PC,
characters.
one, it's like it's working for mainframe also, or it's like only for PC. Like 4K. Does the assembler on the OS version?
Oh, if you make a mistake,
Like click enter on
if you try to define something over 256, the assembler will give you an error. So it will be discovered when you're coding, not at runtime. Did I answer your question?
It's like it was question, does the assembler do the same thing on the OS? Like, does this measurement differ
On the different operating systems?
from Windows to the OS?
Oh, you mean on Windows?
Yes.
You have to look at their assembler, but generally it works the same way.
Mm-hmm.
You're going to find, this is what's very valuable, once you learn one assembler, it's very easy to pick up other ones. So when you get done, you're going to have very little trouble working on assembler or machine code on your laptop or PC programs. So if you want to hack into something, you're all set. You can read the code. Okay. That's what I'm saying is very valuable. So we're going to be seeing this over and over. I don't want you to get too nervous about too much syntax, but here I can define an area of storage. I'm not going to initialize it. I'll just say set aside this area of storage in the program, because I'll be using it for something. The parameters of this are DS. The T is the type. Character, binary, hex. This is the length, how many bytes. So type, length, and then actually number of length. What else? Oh, and you can, if you're setting up an array, that's usually when you use the repetition factor. So I can set up an array of 5 items, each 10 bytes long. 5, type, 10, I'm sorry, 5, C characters, L, 10. That was 50 bytes. Way to set up an array.
Okay. I'm sorry, here would be find 5 times 10 characters.
Yes, so let's say I can do a,
Можно повернуть, пожалуйста, лучше.
Define space.
And DC.
What is DS and DC?
DS
Define space.
sets up the storage
And DC.
and just leaves it blank zeros. DC,
Okay, it's like not empty area. Like if we know what we need to solve.
same thing. You look like an unbeliever.
Okay, yeah. This is.
We'll see some examples coming up. What does the first one do? X.
X is like array of A, B, 3.
Not an array,
No,
just 3
3
bytes in storage. And the contents are initialized to Charlie 1, Charlie 2, Fox 3.
One is defined space, characters, len 2000.
Yeah, here it's setting up 2,000 bytes of stuff.
No,
Можно повернуть.
Часто.
Треба на голову
Poor Roman, he's like in a barrel someplace. You're looking at. Where's this voice at? From the netherworld.
And like the first is repetition.
Okay. Roman, you could just go a couple slides ahead where I have this. Let me talk about each one. You guys look like you're doing it.
And what is the first R? Like RTLN, like when you define space.
Where? Just come up and point.
Third row, third column. It's like, okay.
Oh, this.
I don't know. This one.
Oh, I'm going to explain. All will be revealed. Yes.
This one.
Okay, so here we go. First of all, let's look at the first line. Make sure we entirely understand this. It means something different, entirely different when you define something like this in your higher level languages. For example, what is X? X is the name of the first of the 3 bytes. X is not a field name. So everybody follow that?
Yeah. Okay, and
When you did Python and you gave it a name, like a name of an area, you've got several bytes. That name not only meant a place in storage, but it also meant how big it is. This name is not the name of a field. It's the name of the first of these bytes. It's a common mistake for people to forget that. When I'm moving, real quickly, when I'm doing an MVC, what are these 2 guys? X and Y.
like it's a pointer for the first byte.
Right. Another problem that we have to solve. Bytes are moved is.
Okay, and when we first byte P, not that.
Okay, let's take a look at Z. Z is the first, so what's going on in, okay, here's what's going on. Let's say this was our program loaded right here. So what would this be for address-wise?
X.
000.
Ah.
So X, so let's say that was the very beginning of a program. It's kind of a stupid way to look at it. We will. Okay, so X is the very first byte of the program. So that's at location 000
It's
of
the
our
same
program.
as the A.
Right. So that A would be in location 000.
Okay, the same.
Where would be B? 001. 002. So Y will be at location
003. The start of the space.
good.
Yeah, it's easy.
2000. Now Z is going to be in human.
Why?
What location? It's going to be a relative location 2003. So 1 is, it's getting incremented. And keep in mind, it always starts at relative location. Programmers count from 0. Humans count from 1. We're programmers. We count from.
And what is the first digit in Z? Like Z and first digit after this?
Is it 20 euro?
Hex 0, hex 00.
One more time?
Hex 00.
Ah, okay.
Undefined. So, what's going to happen? 0, I'll just use human. 0, 3, 3, 2003. But how long is this? Because 0 times 5 is,
0 times 5?
yes, it's how much?
Ah,
2003, now what's this then?
8?
2003,
3 plus 2?
what 2?
Ah, it's
3 plus 2000, 2003.
Yes.
So 0, 3, 0,
0. Y is on
3,
3. 2000.
2003,
2003.
2003,
2006.
3.
And when we
This
don't
doesn't take any space. This is where?
the третя, четвърта.
2006,
Okay.
2008,
Mhm.
2010.
Okay, and when we have learned 3, yes, and we added only one character.
So I've given aliases.
Okay. And if we gave 3 and adding 4 characters,
Just repeat what you said, please.
our
Last one line.
last line, we have line 3, and we made 4 characters length.
That's because you don't want other people to understand your program. It's just a bad code.
Ah. Nice.
What does the blank line?
So you keep your job. I show you tricks, how to keep your job tricks. Nobody wants to touch this program because it's horrible coding.
Line 3 and
Now, you won't lose your job. On the other hand, you're not going to get promoted. Because you're the only one who knows how this stupid program works.
But it seems not to work because 3 line 4.
Hey, this is assembler. The assembler says this guy's coding the assembler. Smart person. They know what they're doing. You follow? Oh,
I have a question.
yeah.
I don't know, this is kind of assembly.
Okay.
So,
Oh, I'm in trouble, I can tell. Yes.
it is size 0.
Yes.
And
It's the size.
you say that Z and A has the same offset.
No. Z has this offset of 2003,
Yeah.
and then this is 2000, wait, 2003. It doesn't increment. This is 2003.
Yeah.
Uh-oh. 2006.
Yeah, that was what it is.
Okay, yes. But I kind of,
Yeah, it's
I confuse anybody other than myself. Thank you. This is not the best example. Here's where you usually use it. Wait, real quick.
and on Windows is like in the another way.
No, it's,
No, Windows is
syntax is a little bit different, but it's same way. You're completely on your own. Machine decides, you know what are you doing. If you're doing something wrong,
You're using assembler. You must really have something sneaky in your mind.
so my question was just about some syntactical nuances, some details, not about the year.
This is, I went 3 slides more. Let's take a look. So this is if the very first byte of the program is at this location. That's a 0, location 0. It is 3 bytes long. So X is at 3. 4 byte area,
Yes.
7. So name is now, who's the only one paying attention to these names? You. These names are not going to show up in the computer.
0 times
So
4.
name is another, what the computer is going to do is take name and replace it with a 7.
0 times 40, and this 0.
So 0 times anything is
0. And the And why?
Because in my program,
So,
I can refer to name, or I can refer to first name. Last name. Or I can refer to, I can do this, just again, like you want to keep your job, give you tricks.
Можна було.
Ти ще нічого не встиг.
А то повинно бути знайомо з вказівників, ну це
так, таке нічого, мені нічого не каже просто.
Ти не бачиш?
То не складно, просто багато.
А, тут просто це вже проста річ.
What is another name for last name? Hex 11. Or that same location I could refer to as So there's lots of ways to write assembly. And that's what I'm showing. Good?
Why 7 plus 10 is 11?
You're not supposed to be human. So what's on the left? Is that human? It's hex.
Йо,
10 is A.
So, play. Yeah.
A plus 7 is 1, 1.
Та я просто подумав, що це...
Roman, do you know this, or are you gonna...
Yeah,
See, Roman's a computer, he's not human. That's why we're doing assembly. Assembly is not for humans. Like aliens coming from the moon.
Let's look at the rest.
It's a full moon also, isn't it right? Yeah.
This is the
You're just a little bit tired then.
How you guys doing? Anytime you want, I got stuff to last for about 12 hours. So let me know when you're, Roman, is everybody else online?
No, only Roger.
Okay, so if you guys get tired, just let me know.
How much slide we have? More.
A couple hundred left.
Nice.
Я не знаю, я можу щось.
Я, давайте щось не розкажу.
Давай, 20 minutes.
That means 400 slides in this presentation.
How many?
400.
Oh, nice.
Now, I'm not going to do all 400 in this class. My goal here is, I'm trying to get you to this sort of level that IBM thinks their challenge people can do. So there's a program program that IBM has for college people, university people, and they call it the IBM Challenge, I believe.
Yeah, it looks like.
Something like that, IBM Challenge, and they give you a bunch of tasks. And what they require, they have several languages. They have assembly, COBOL, Rex, REXX, and what was the other one? And JCL, I think those are the only ones. And what they're requiring you is just to read these programs. But I'm trying to get you to be able to write very simple routines. I don't think you guys are here to become assembly programmers.
Why not?
Well, you can be, but this is not the class. I would go through all these, and I'd even have a second class with about a similar number of overheads,
Jim,
if that was your job. Yeah.
there may be small misunderstanding. They were talking indirectly, in fact they kind як натяк англійською. They were indirectly talking that they a little bit tight, that maybe half an hour is enough for one lesson.
Yes.
They were mean that, and not the total volume
Yeah.
of
Okay.
materials.
Yeah.
It's not a problem. They like to know assembly and
Yes. Yeah. So I'm trying to get your goal. When my goal here is in each one of those languages to actually be able to code some very simple routines. And if you could code something simply, you'll probably be able to read a much more complicated program. So that's kind of like my goal with this series of stuff. Think something like you'd be interested in?
Of course.
Roman?
Hey,
Прийом.
Yes.
Every time, yes. Записав на тебе.
Yeah, I taught grad students this other place, and what I noticed is you guys are undergraduates now.
Yep.
And you'll see by the time you get your graduate degrees, by then you'll be able to smile, nod, and blink your eyes, and actually sleep at the same time.
I'm not
So they're always
sure.
very readable.
Jeff,
They're nodding, smiling.
I'm not sure if they would, because my scanners are sensitive enough to see it and punch a little
You go,
bit. Yeah, and I often do this during my lectures, so not that great chance.
Парку кидати.
I'm not sure. I have to.
Well, how
think
about this?
first.
Is this a good stopping point?
No.
Oh,
You
yeah.
can make.
It's like 20 minutes more.
Yeah.
20 minutes more.
Oh, okay, good. So there's
Може бажаємо застосувати комп'ютер vision, щоб він Рома не повертав сам. Я не думаю, що поставити з камери.
Сходимо тренувати.
Ні, краще лампочку на чоло, і коли дивишся туди. Ой, камера.
Не надо так.
I didn't mention, but these names here, the DS, org, DC, those do not turn into computer code. They are instructions to the assembler. So they're telling the assembler, hey, increment 3 bytes, and later on I may refer to the first of those bytes as W. Name is the first one of these 30 bytes in memory. Org says, hey, I'm gonna restart this. I'm gonna restart this from name. I'm sorry, yeah. So I'm sort of giving another name, sort of giving an alias to this byte. I could call it in my program either name or fname. And we'll do this org. Later, we're going to see before I did this with, remember I did it with a 0? Like 0 CL30. Okay. When you usually use this org, you're setting this up as sort of a pattern. And we'll talk about this pattern in a couple of occasions, but one of my goals is to do re-entrant. Talk about re-entrant code. And you're going to need this sort of pattern for that.
And when we use this originate, we have to put only a name, or we can use like this location by number.
You could use any words you want to.
No, like he is asking, can we use location as operand for org?
Can you write org 10, for example?
No, because the whole idea is that you, you can't use a number here. You have to use a position here. That's what org does.
And
Org resets the counter to this.
To the previous one.
Or name could have been up here. So it says whatever was up here, org says,
Before the name.
reset this to 0. here's what they did. We have a report line. It's 80 characters. And then what we want to do is, how many bytes for each one of these? So we got a report, and it's going to have Monday, Tuesday, Wednesday, Thursday, so forth.
Okay.
And each one of those columns will be 10 bytes wide. And this is the way to set that up.
Yeah. And how should we write the report like?
When we send it, so what we're going to do in the program is get data, put it into these storage areas,
Yes.
and do a put, and point to the, we're going to put file name buffering.
What next? Problem.
Pointer. What's this guy called?
Okay, and file name, buffer name.
Up here, you're going to do an open. Oh,
Open file, put it into the
Open.
buffer. Okay, I understand. Хорошо.
then we'll have,
Like we put the whole file into the buffer and
Yeah.
then to the.
so you put the data into the various places and you write it out. Now, these are macros. You're going to write one line, it's going to go to the macro library and say, oh, here's a whole bunch of assembly statements. Oh, very good. So, finally, we're going to get to an instruction. Now, the instruction is going to be called move characters. Unfortunately, it won't move anything. It's going to copy. Even though it says move, it's actually, like if I move, I'm not there. But for the computer, it doesn't work like a human. If I move myself in the computer, I'm still there. MVC XY. There's a number of ways to code this. First of all, the assembler I'm sorry, I just forgot the next overhead. Okay. This is a move character. It's going to turn into, so this is the format. There's several formats you can write the move character in assembler. But no matter how you write this, what format you use in assembler, it's going to turn into this. Now, what does this say? It'll be the opcode for move character. Now, it's gonna, three things that have to be known. Where the bytes are coming from, where they're going to, and how many. Good, how long. So that's what's gonna end up here. So let's take a look at this. This will be the opcode for MVC, which I forgot. If you do this a lot, you start remembering. So this is going to be the MVC opcode. In that earlier statement, how many bytes am I moving? So let's take this guy. I'm moving 4 bytes.
And what is in the brackets? 3 and 10.
So this is the length.
Mhm.
But you're not human. You start counting from,
0.
so this won't be 4, this will be 0, 3. See, the assembly gives you lots of opportunities to make mistakes, especially when you start thinking human. MVC opcode, 03, base, displacement, base displacement. So it's going to go to this register, get the address, add this displacement, and move it to, the first byte will be moved to the contents of this base register plus this displacement. Yeah, magic?
No. We are computers, so no way. 4, 3. Needs that.
We're going to end with this.
Okay.
But I'd like, so somebody who has a Windows computer,
Right. Let's go.
you want to try this here?
To move.
No. Just install this and see if it starts. Okay, I didn't have enough time. I don't have a Windows computer.
Roman have Windows on his computer.
Oh, Roman, you have Windows in your computer?
No, I don't have
Ну що ти?
Linux.
Що ти не можеш?
What OS are you using?
Fedora.
Федора.
Oh, Fedora, right? Yeah.
Та в тебе ж була війна.
Я вибрав із низ.
Та ж, конечно. Окей, ну добре, я запущу. Хорошо.
Okay. No,
Потім тобі покажу, як вона не запускається.
Okay, I will try it at home.
good. Okay, so I've got 2 pieces of software we could try. Here. Okay, what?
Maybe before we go on, I have a question because I'm
Oh, yeah.
not sure. It is the number of register or there's a 3?
Yes, that's the register, and the 12th, that's why I want to go through that again, because everybody's like, you're all brain damaged by now. So the next class, they'll have fresh brains, new synapses, and that's what's going on. 12 is our base register, and it's going to move 3 bytes. 3 bytes, I'm sorry, whoops. It's going to move
4 bytes.
4 bytes.
Ah, you're human.
And one is at offset 8, and the other is at offset 4.
Why you ask? Several weeks ago I have read about PowerPC, another IBM architecture, and they have strange, as for me, habit not to write register number 3, but just write 3.
Yes.
You always get lost of those numbers, so it's
Yes.
is a question.
I'll show them how to code this stuff later, so you can reduce mistakes like this. Because I know even though they're nice people, and they're really computer people, they sometimes revert to humans. And so we'll give them some hints that'll help humans, their human side. And then, let's see. Oh. Okay, whoever has real quickly.
Хто придумав?
Where's that? 390.
What do you want to open? Assembler concepts?
The
David Woolbright homepage.
no, see the Woolbright, that would be 1. That ought to work on that's a Java program. And if everybody could put that on their machine.
Java like ID, virtual machine.
No, it's gonna be Java, a Java program. So as long as you have Java runtime, that's all you need on your machine.
To run this simulator.
Господи, я навіть тут так.
No, next class.
I need to bring my Windows PC?
Well, if you can bring your PC and Roman's gonna do the same thing.
Я Windows хочешь ставить.
So everybody needs to go to this Woolbridge. Darn it,
Just походіть поставити.
part of my problem here.
Ні, так це на Java, я буду чому запустити. Скажіть, що симулятор на Java написано.
There's
Це GM.
Oh my goodness, I can hardly see this. Can you guys see this?
I see on the assembler COBOL. I see assembler. Down. I was, yes.
Yeah. Oh, I can,
Assembler.
no, not the assembler, back. This is,
Ні, розумієте,
Visible resources, student Android projects, PIX, person.
it's like a,
Розумієте, воно стане краще. Не сильно нам все. Контрол колічу.
you know what? I'll go home on. Oh, very good. What is it?
Prisoners and words PIX student. Visible resources.
Okay, install Visible Z, if you guys don't mind. Okay, it's a Java program. I don't think you're gonna have any trouble with this in this guy's.
Okay.
Okay,
I will try it at home.
yeah.
Probably it could run on my.
This should run both on Linux. Yeah, it's gonna look like this when you get done,
Eclipse.
when you start executing it. So this will give us a chance of looking at some actual code and see what it's gonna look like in the machine, because that's my whole objective here, is to make sure you get an idea like how this stuff looks inside the machine.
Okay.
Okay. But this has a number of restrictions, a learning aid, but there's another one that runs on Windows, and I will write, who's got the Windows computer?
I have.
You have, maybe, I don't know if you got time to screw around with this. This other package, this is the Z390. Let me see if I can.
Visible different.
And that's, I haven't tried that, but it looks like a lot of promise. Are you online?
Yeah.
Oh, do a Z390 emulator,
Так, вот.
yeah. Yeah,
This one.
yeah. And there's a Z390. Yeah, let me try this.
Different here.
Yeah, there's also a Z390.
Demo columns.
Well, this really works with Windows. They wrote it for Windows. And it looked like the Linux install was a real problem. So you go to this z390.org. Let's see. I think it's this. No. Yeah, it's on source, but there's also like a viewer of this whole thing. But if somebody could download this, yeah, and just install it and see what happens. I know you're real busy, I need to. See, my wife has a computer, but if I touch it, like, I'll come here like with arms in a sling and everything else. I'm just looking out a couple slides. Yeah.
It's interesting for me too. It is. Не підійшла.
Ні. Я не знаю,
Я ж статива не маю, правда, я ж думав, що маю.
можливо, це напис.
А, ви собі розпізнали.
Що не признаю чужикам.
Ой, боже, рамочку тут зараз буде знову скинути.
Здорово!
Привет.
Next.
Прекрасно.
Oh, here it is. This is what I wanted to show.
Всі уроки.
Ще це навчання і вже будете тут. Всі.
Так, це не надовго. Не важко. Одразу половина.
Хто буде виганяти людей з бізнес-іонів?
Так, бачите, у вас імунітет, вам добре.
Офігенний курс, в принципі, організація дуже легкий.
Сам вера,
Мене був жай.
Okay. So this thing is a 390 emulator.
It doesn't work out of the box, I'm thinking.
Okay.
I'm not sure, it looks like it doesn't write correct path to Java, and so I tried
Yeah.
Скріни.
no problem for this, but it doesn't run.
There's a couple demo programs in.
Тримай сонечки.
I need to run it manually.
Yeah. Don't spend much time on it.
No, I hope it will take the program. It's installed using
Yes.
predefined Java path, and Java here is not at that path. So
Oh, okay. That's what it is.
Так, тепер треба цей моторчик на SSH.
Find my Java.
Іди ти знаєш, куди воно не запустило. Тобто я сьогодні ми настроїлися, Саш.
To find Java interpreter manually and
Нам
just
треба
paste
магнітики знайти.
Магніти. А в мене є ці, і я купляв, щоб на дошку забляти.
А, ну так, класно. Ну, то у нас дуже класно захист буде аудиторії.
А книжки, коротше, хороші.
Here is this simulator. What to do next?
Не добавляв.
Подожди, Миколай.
Звісно.
I don't know. Oh, okay. This is the start.
It's using a trans, but with some magic. It's written wrong path to Java interpreter. So you just need to paste manually where Java is.
Клас.
It's not a
Okay, there's probably a bat job, some demo bat.
Російський. 99%. Лучше.
Like it looks like there are some interpreter errors because there are many
Yeah.
messages about
Yeah.
Java errors.
Mm-hmm. Oh, here it is. Still this view.
Чекай, і Юля, як ти ж є роки навчиться в Києві?
Не знаю.
Наприклад, в Львові вчитися? Ну, фотографія, звісно, класна.
Oh, okay.
Так, що мені треба ставити на свій ноутбук?
Someone else wrote a program that works on Windows that does a view of this. I'll find that and send it. We'll get it next time.
It's some problems with Windows later. But those periods should
But this looks, and started.
And what should we use on Linux or?
No, I saw the Linux install. I didn't even want to try it. It just looks so confusing. So it seems to work on Windows
Okay.
well. And maybe we can together write a program or something like that. I figure out something.
I will look for them and maybe develop some guidelines for students how to run it.
Yes.
Well, have some experience to run exotic programs,
Yeah.
exotic architectures.
I will then install Windows on the computer and then install it.
Потім
Oh,
себе
okay.
полетять
What do you do, a dual boot?
Yeah.
Oh, that'll be excellent. Good.
But I hope I can get run it in Linux. I'll try. And if it doesn't work, so
Okay.
you can.
Окей.
But if we can get this working, then we can do, because these guys did it on, this looks like a whole bunch of old mainframe programmers. Just got together, they're retired, and they just, let's make one. So that's what it looks like, and they've, you notice like up there, they did a write to operator that's similar to write to the message screen. You know, like write this out for Linux.
I hope we can try. Maybe it looks like it needs some more tinkering with passes and whatever because it's not that good installer.
Yeah,
It messed it.
Yeah, that's it.
I'll check it. Maybe
Yeah.
it is would not be a problem. No?
good. Good day today?
Yeah.
Learning took place? I forgot the name.
Все.
Папа, Ромчик.
Goodbye. Bye-bye.
That's all for today.
Yeah.
I work with it and we see. Юра, I mentioned I forgot his name, Воробьев mentioned that he got access to console in those our course, online course, but I haven't found it. Do you know how it looks like, where it is?
Віталік казав, що десь
А, Віталій.
Я зрозумів, спасибо тебе, Воробьев.
Я просто не знаю.
Напевно, I
Ah,
can write.
so where is he?
Я йому напишу.
І в нього комісія.
Ну, хай покаже, де вони є. Ви прислали, я не дуже той, але я так пройшов проклацав ті курси, я там не побачив. Там. Може я якось не так це роблю.
Окей, ми його запитаємося.
Окей? Ви як? Ви йдете зі мною чи?
А ви зараз
Це
йдете
Ветро.
на цей ветро? Йдемо сьогодні чи завтра?
Можливо, відкричати, бо я не...
Окей.
А вам як?
Ні, мені підходить завтра, бо вже всі плани змінилися.
Окей, який час тоді завтра?
Кажи.
Там, бо я там на 6 маю точно зустріч, то можемо 12 допустимо.
Так.
На 6 вечора.
Я вже
Ні, ну кажіть, 12, 1, 2, 3.
кожен раз.
Так, давайте 12.
12. Окей, то тоді завтра.
Давайте обміняємося.
Так, тоді. Я вам щось покажу.
Я просто починаю, а до розетки нормально підключати?
The machine card went on
Yeah, I think today is.
yesterday or the day before.
Can you
It
repeat?
broke the machine card that I took a ride on.
Is
For yesterday.
every day.
It broke.
Про.
All of a sudden, the guy stopped and got excited. And what happened, he's talking to his wife or something, and got all excited, and he jams the thing and pops the clutch, and you hear a crack. It was like a drive shaft. It was like a big deal. Drive shaft, it was like dead. So everybody got off. He was offering the 5 beer, yes, I didn't take it. I felt so bad for him. You know, 'cause, I mean, the guy's just working, and all of a sudden his machine goes dead.
And how you got home?
I walked. So it was
Was it far away from your home?
It wasn't that far, but at one point, one lady told me, over here, and got another marshrutka. It's like following her, and she just spoke Ukrainian.